So today I want to talk about how do we get to artificial general intelligence. We've been really good at building on artificial intelligence, but not very good at building artificial general intelligence. We've been promising it for, I don't know, 50 years, 70 years, but delivering on it is something else. So back in 1956, the notion of artificial intelligence, the phrase artificial intelligence, was first proposed in a grant proposal by John McCarthy, this fellow over here. And he organized a conference at Dartmouth College for the summer where people would come in and work on artificial intelligence. The hypothesis was that summer ought to do enough to help us make a lot of good progress on delivering on anything that a person could do. Herb Simon, who was one of the people who was at that conference, presented a reasoning system at the conference that actually wasn't received all that well, but it could reason. It could do mathematical proofs, and it in fact found some proofs that hadn't been known before. And his hypothesis was that the range of problems that computers could soon handle within about 10 years would be coextensive with the range to which the human mind has been applied. Well, that was 1958. And then a few years after that, I.J. Good wrote about an ultra intelligence. And his argument goes like this: let an ultra intelligent machine be defined as a machine that can far surpass all the intellectual activities. Since the design of machines is one of those intellectual activities, an ultra intelligent machine could design even better machines. There would then be an intelligence explosion. The intelligence of man, and I suppose of women too, would be left far behind. Thus, the first ultra intelligent machine is the last invention that man need ever make. Well, that hasn't exactly happened yet. But still, people are expecting it. Martin Ford did a book, came out, I think, about last year. He did the interviews in 2018, and he interviewed 18 prominent artificial intelligence researchers. They're listed over here on the right. And when I say prominent, they are prominent. They agreed on a range of dates by which artificial general intelligence would be achieved, somewhere between 2029 and 2200. Then what's even more important is he asked them, what do they think is needed? And their answers included things like more advanced neural network, deep learning systems, new methods for extracting knowledge from natural language and unlabeled data, new knowledge structures that can be used to support reasoning, importing knowledge from neuroscience and other areas, symbolic logic, imagination, and invention. Well, they got some of it kind of right. I mean, all these things are probably necessary, but they're not going to be sufficient, I would argue. Gertzel and Yu said that we're going to need things like video game agent control, mobile robotics, genomics, natural language dialogue, theorem proving, and program learning. And they thought they could maybe do that within a decade or so. And that would somehow get us towards artificial general intelligence. Now, on the other hand, there have been people arguing that we could never achieve artificial general intelligence. So for example, they've said, well, it's a quantitative question. How general does general intelligence really have to be? Well, if we can get a computer to do two things, is that more general than a computer that does one thing? If we can play 6 video games, is that more general than playing one video game? How many specific problems can we solve? And all we need is a bigger computer, and we'll be able to put the solutions to each of those in there and solve different problems. Then there are people who say that it's just impossible. and people like John Searle and Hubert Dreyfus, that computers lack some quality that humans have. Searle, for example, says that only brains can have thoughts that are about something, that computers are only capable of syntax, so therefore computers couldn't actually have any real thoughts. They could only simulate having thoughts. And Dreyfus had something to do with consciousness, and it's never entirely clear what exactly was the limitation, but humans have it and machines can't. Therefore, machines can't be thoughtful. They can't really have intelligence. Then there's another group that says, oh, there's no such thing as general intelligence. It's a statistical artifact. When the notion of general intelligence first evolved in psychology, the idea was when people take intelligence tests, if they score well on one subtest, they're going to score well on another subtest. They're likely to score well on another subtest. But that doesn't mean that those subtests all share something. It doesn't mean that there's some general intelligence that we tap into for each of the subtests. Maybe there's some statistical artifact that does it. So we can't achieve artificial general intelligence if there's no such thing as general intelligence, just specific intelligences. And related to that is the idea that intelligence is not a thing. It's not something we can achieve. It's not cohesive. We don't have a definition for it. We don't have a good idea of what we have to do. We have all these specific skills, but is there some difference between skills and intelligence? Yeah, there probably is, and we don't know what it is, and we're never going to achieve it. Now, probably the most telling one is the one that limits us today in the strongest way. And that's the idea that general intelligence is just a stacking of specific intelligences. It gets back to the quantitative question. How many different specific intelligence do we need? We can be really good at playing Go. The same computer could be programmed to play Go and chess. The same computer could be programmed to do any number of other things. Is that computer generally intelligent? And all we need is more. We need bigger computers. We need a computer with the capacity of the human brain. Once we have that, intelligence is inevitable. And so we don't really need any kind of general intelligence. All we need is to stack up a lot of specific intelligences. And all we need to do that is a computer with the computational capacity of the human brain. We can predict when that's going to happen. That's probably going to happen within the next 10 to 15 years. Not a problem. We're all done. It will just happen. The Terminator trope works that way. In the Terminator, they turned on Skynet, and a few hours later, it had achieved enough intelligence on its own to take over the world and decide that humans were a threat to its existence and needed to be destroyed. That's not a very, it makes good fiction. It's not a very likely story. I come back to the notion of foxes and hedgehogs. So Archilochus said in Greek, and unfortunately I don't read Greek, that a fox knows many things, but a hedgehog knows one important thing. We've been really good at building hedgehogs. We have hedgehogs that will diagnose cancer. We have hedgehogs that will answer the telephone, that will make us appointments. We have hedgehogs that play games. But what we need is a fox. We need something that will integrate over all of those and provide a higher level of intelligence than each hedgehog. Each hedgehog may in fact be brilliant, but it's not quite the same thing. So these are the kinds of things that we're really good at right now. We're good at image recognition. We can recognize and identify the objects that are in a scene. So here we have a person and a laptop. Unfortunately, we're missing the elephant that's in the back of the scene. We can identify books. We can identify cancer lesions and distinguish them from other kinds of skin problems based on photographs. We can do mammogram analysis. And we can do that with a level of accuracy that is at least as high or higher than physicians can show. We're really good at game playing. A few years ago, when the company that's now part of Google was able to play Go at championship levels, some people argued that was a breakthrough in general intelligence. But really it wasn't, because that same computer can't even begin to play chess. It could learn how to play chess, and that's the kind of thing they're working on now. But it was a specific intelligence specific to playing Go. A lot of great invention went into it, but that's not quite the same thing as being generally intelligent. We can play chess at world-class levels. We can play video games at world-class levels, and we can do text analysis at really high levels. So here's a little excerpt from GPT-3, and there are people who argue that that program is a sign of general intelligence, but really all it is something that has learned patterns of language production. And given a place to start, it can produce language based on that place to start. So the text from which you want to start. But it's not general intelligence. It is sophisticated, powerful text analysis. Now, a reason for this is the focus on things that are easy to do, or at least not too hard. So Go was too hard for a long time because the number of choices was so high, not because it was conceptually difficult. It's that the number of choices that had to be explored to evaluate whether you're making a good choice or not was much too high. So people figured out a way to get around that. And people built heuristics that would limit the range of choices they had to make. But all this started with chess as a Drosophila of artificial intelligence, in the sense that if we can master games like chess, games like Go, then we will be fully knowledgeable about the nature of intelligence. So today, we can play Go like a champion, but we still have trouble building a machine that will fold laundry. So on the right-hand side is the state of the art for t-shirt folding machines. And in order to get your t-shirt folded, you see at the top, it folds them very nicely, but you have to put in the t-shirt just right for the machine to be able to do it. T-shirt folding is really, really hard, even hard compared to playing Go. So we've had a lot of success on well-structured formal problems. These are problems that are characteristic of Western intellectual achievement. These are problems that involve deliberation. They involve systematic, logical thinking. We're great at those, but we're not very good at more informal things like walking across the room or folding t-shirts. We're starting to make some progress on robots that can walk across the room, that can pull out conversations in a crowded room and so on, but those are still hard. If we don't change our ways, winter is coming. You probably know there's been a lot of AI winters. About every 10 years or so, we get too far out ahead of our skis on the hype cycle. We promise that we're going to deliver general intelligence within the next few years. And when it doesn't show up, people get discouraged. The funding agencies get discouraged, and problems go away. Funding for the problems goes away. Now, we're a little bit better off in that by focusing in on narrow problems, we continue to do things that are economically viable. AI is economically useful at this point, but achieving general intelligence, we're not even heading in the right direction. It requires a change in road and a change in the way we think about general intelligence. And that's really what I want the focus to be for the rest of our time. We have been focused on one little bunch of problems and getting really good at solving those, but they're only a very tiny subset of all the possible problems that we might consider. Mathematically, all current machine learning, and artificial intelligence has to involve machine learning if it's going to go beyond what we teach it to do, what we program it to do. All current machine learning consists of three parts: an input part, a model part, and an output part. Another way of saying that, it consists of a representation, it consists of an evaluation, and an optimization. So the representation is, how do we structure the problem? How do we set it up in terms of models? What constitutes the inputs? How do we change whatever the world is into numbers? How do we operate on those numbers? And how do we produce an output and then translate that output into something in the real world? It has to have an evaluation. How do we assess how close our model is to what we want it to be? And then optimization is, how do we adjust the model to get it closer to the solution? So all machine learning consists of these three things. These are the only things that a machine learning system can think about. It can think about the input, it can think about the model, and it can think about the output, but it doesn't think about anything else. This is the range of stuff that it can think about. So what we have to have in order to have some progress in our current machine learning paradigm is a kind of reductionism. How do we take a complex problem like playing Go and reduce it down into something simple that a computer can do, like navigating a tree structure? So Doug Hofstadter, whose name came up earlier today, in 1977, for reasons that I only just recently learned, said this, that there may be programs that can beat anyone at chess, but they will not be chess programs. They'll be programs of general intelligence, and they'll get bored. You'll say, do you want to play chess? And the computer will say, no, I'm bored with chess. Let's talk about poetry. That's what, in 1977, Douglas Hofstadter, the author of Gödel, Escher, and Bach, that's what he thought it would take to solve the chess problem. Very soon after he said this, though, as he notes in an essay that he wrote some years later, people began to figure out how to reduce chess into a tree structure. Instead of trying to figure out the psychology of one's chess opponent, what you really need to do is figure out which is the right choice to make in a tree. Once that was figured out, it became possible to make programs that would play chess at world-class levels, because we could reduce a complex problem to a, quote, simple mathematical form. Go is really complex in the sense of the number of alternatives, but it's not very complex in the rules. There's only like 9 rules to all of Go. So where do these representations come from? If we have to have these representations with the 3 parts, where do they come from? Well, right now, they come from people. And among the top of the people who produce these representations are these 3. Hinton, Bengio, LeCun. They won the Turing Prize in 2018 because they thought of new ways to represent the problems. And I love this picture with all of them gesturing here and there. They make clever designs. Clever people make clever designs. We need to get past the need for people in this. If it takes people to make clever designs, we're never going to have general intelligence. What we need is to change from making hedgehogs into making foxes. So here's an example of a problem. And it starts to demonstrate how we simplify the problem and then how we might elaborate on it. So it's a hobbits and orcs problem. 3 hobbits and 3 orcs arrive at the side of a river. There's a boat at the side of the river. They have to get across. The boat will hold 2 organisms. And if ever the hobbits on either side of the river are outnumbered by the orcs will kill and eat the hobbits, and we don't want that. If they're not outnumbered, then everything will be okay, and they're otherwise trustworthy. So Saul Amaral figured out how to make this into a mathematical representation that could be operated on by a computer. And this is the kind of thing that a computer can solve straight away. There isn't a big issue with being able to solve problems like this. It's a formal problem, and it has good structure. Now we've got another problem, the missionaries and cannibals problem. There are 3 missionaries and 3 cannibals that arrive at the side of the river, and they have to cross. If the cannibals ever outnumber the missionaries on the side of the river, they'll eat the missionaries. What are they to do? And you can probably recognize that this is exactly the same problem. All I've done is I've changed hobbits to missionaries and orcs to cannibals. And if you can figure that out, you can say, oh, the same method I learned for the hobbits and orcs problem, I can apply to solve the missionaries and cannibals problem. But how do you know how to make that transfer? Okay, so what if they all wore red hats? Oh, that's not important. Well, how do you know that? What if there's an island in the middle of the river? Does that change the problem? It changes it dramatically. It makes it far easier to solve it, because you just don't want hobbits and orcs. You don't want the orcs outnumber the hobbits either on the island or on the riverbank. And now it makes it easier. How do you know the difference between what if they wear red hats and what if there's an island in the river? How do you know which of those is important? Does the boat have oars? Well, I didn't say the boat had oars. The picture I showed you had oars, but if I just wrote down the description of the problem, you can assume that the boat has oars. But how do you know? Why can't the people just wade across the river? Well, I wouldn't ask you this question, but how does a computer know that I wouldn't ask you that question if they could just walk across? What if it's winter? What if instead of the cannibals eating the missionaries, what if the missionaries converted the cannibals so they were no longer cannibals? Well, now you can go any way you want to go because nobody's going to eat anybody. How does the computer know this? These are the kinds of problems that we need to think about solutions for. What if 4 people of each type arrive at the riverbank? It turns out that makes the problem insoluble. If 4 people of each type, if 4 missionaries and 4 cannibals show up, it's not a solvable problem. Here's another one, one of my favorite problems. It's called the mutilated checkerboard or mutilated chessboard problem. And the question is, can you arrange dominoes to cover a mutilated chessboard? Now, every domino covers exactly 2 squares. And so if the chessboard was whole, you could easily cover it with dominoes. But there are 6,728 ways to arrange them, but you could do that. You could do it by brute force. But it turns out that you can't tile a mutilated checkerboard with these dominoes. Now, how can that be? How can I know that? There's 62 squares. Each domino covers 2 squares. Well, that ought to be possible. Let me try some ways of doing that. It turns out you cannot. And why can't you? Easy insight reveals the solution of the problem. Every domino has to cover a white square and a red square. But there's 2 more red squares than there are white squares because we've taken 2 of them out. And insight makes a hard problem that could be solved by brute force, but hard, makes it into an easy problem. How do you get there? Here's another version, the ants tour. Imagine that there's an ant that's crawling on the checkerboard, on the chessboard. And it only goes left and right, up and down, north, south, east, and west. Can that ant visit every square exactly once? And think about that for a minute and say, well, if the ant is going left and right and up and down, it has to go from a red square to a white square. Or it has to go from a white square to a red square, but there's more red squares than there are white squares. So the ant can't do it either. But how do you make that transfer? That's a problem that we need to solve. Here's yet another one. This is called the knight's tour. A knight in chess can only move in certain ways. So it moves it can go up 2 squares, 1 to the right, up 2 squares, 1 to the left, left 2 squares, 1 up, left 2 squares, 1 down, and so on. And it is possible to do a closed knight's tour on a whole checkerboard, whole chessboard, but is it possible to do that on a mutilated chessboard? And you might think about it. You might think, oh, there's lots of ways of doing that. We could draw a graph. We could do we could solve. But it turns out that just like the ant and just like the domino, every time the knight moves, it has to go from a white square to a red square, or from a red square to a white square. Now, how if you have that insight of you have to have the same number of red squares and white squares, that allows you to solve all these 3 problems. But the trick is, how did you get that insight? Can you select that insight from a bunch of other insights? And how do you know whether it's going to work? How can you predict it? How do you actually do that kind of stuff? That's the kind of problem we need to solve to get artificial general intelligence. Well, here's another problem. Edgy's ant. Can you, by going left and right, up and down, cross every edge? So go from here to here, here to here, here to here. Can you cross every edge of all the squares and do that exactly once? You say, oh, well, you already told me there's you have to have the same number of red squares and white squares, and so therefore I'm going to say no, you can't. But that's wrong. The number of red squares and white squares has absolutely nothing to do with it. Instead, it has to do with the number of edges that attach to each square. And this is an Euler circuit. And so the transfer, the knowledge that you gain from solving the first 3 problems is of no use to solving this one. Rather, it has to do with, there has to be an even number of edges on every square, and there isn't. So there are 3 ways to address the mutilated checkerboard problem, the original one. There's brute force, that's hard. If you have a 12 by 12 square rather than an 8 by 8 square, you know immediately if you use the red and white, the need for equal numbers of red and white, you know immediately that you can't solve a mutilated 12 by 12 board. But if you want to do it by brute force, it's like 4 quintillion possible arrangements of dominoes on that. So brute force can be hard. Logical proof turns out to be hard. John McCarthy said it was a tough nut to attack. But if you know the color pair that you have to have a red and a white square, that's easy. Then there are other kinds of human insight that's necessary. You may know about this Henri Poincaré quote where he was talking about how he solved some mathematical problem. He went off on a bus tour. It was a geology expedition. And he says, it just came to me how to solve a problem, that the problem I was working on was like another problem that I already knew how to solve. I didn't have to verify it. Eventually it just came to me. Well, that's how we're making progress in artificial intelligence, because things come to people like Hinton. Archimedes' insight, you're probably very familiar with. He had to decide whether a crown for a statue of one of the gods was pure gold, or whether it had been adulterated with silver or something else inside. And he couldn't figure out how to measure precisely the volume of this complex kind of shape. They show it as this kind of crown here. But then he got into the water and noticed that when he got in the water rose up, and he figured, oh, if I can do that, I can figure out how to solve this problem by measuring the amount of water that the rise in water is proportional to the volume. I know what the weight is because I can weigh it. And now I know what the volume is. Now I can solve this problem. And he's said to have yelled Eureka and run down the street naked. Something more modern and more mundane are Feynman diagrams. Richard Feynman was a physicist who won the Nobel Prize in part for making these diagrams. Where other physicists would write complex equations, he figured out how to basically make cartoons. And Frank Wilczek said, if not for those diagrams, he couldn't have won his Nobel Prize, because the problem would have been unthinkable. So how can we come up with representations that make problems thinkable? So here's just another one. Gerard and Paul were born to the same mother on the same day in the same hospital, but they're not twins. How could that be? They're triplets. But how do you change that representation to think about it? The way we're approaching it now is what we need is a bunch of hedgehogs, and on top of that, we're going to put a giant hedgehog that will supervise them all and put them all together, and somehow this stack of agents will be able to solve problems. That basically assumes that everything that can be invented has been invented. We have enough agents, or we will have by then, to be able to solve any kind of problem. All we need then is another agent that figures out which agent to apply, and that's probably not going to actually work because of the combinatorics, because we can't have a complete set, because there's no free lunch. Overall possible problems, any learning system is going to be at chance. And the number of combinations you have to make, you're going to be lost in thought forever. So what we end up saying is that a stack of hedgehogs is not the same thing as a fox. The problems we can solve are path problems. Can we find a path of adjustment through a state space? Can we get something that's probably approximately correct? Can we find something that allows partial solutions? Can we measure progress? But what we need, in addition to all of that, are insight problems, where, like Poincaré, we can suddenly recognize a solution. We can't measure how close we are. We have to change the way we think about things, like the checkerboard problem, like the chessboard problem. There aren't any partial solutions. He didn't say, oh, I've got part of a solution to the problem. There's no obvious indication of progress, but somehow we need to be able to solve both kinds of problems. That's what we need to be able to have artificial general intelligence. So what does the road to artificial general intelligence look like? Well, we have to be able to address ill-defined problems. We have to be able to extract overarching principles. We have to create new tasks. Who invents these tasks? Who figures out how to map the problems into representations? The computer will have to solve that problem. It's going to be generally intelligent. We have to be able to compare models. Is this model better than that model? All we can do now is navigate through a model. We have to transfer learning, but as you've seen, transfer isn't always obvious. Sometimes we have to work very hard to get our transfer. Ultimately, what we have to do, and this is probably the single most important thing, is create representations. We have to create representations that solve problems by making them solvable. Right now, computers cannot do that. Computers have to be able to do it if we're going to have artificial general intelligence. We have to be able to resolve ambiguity. We can do a little bit of that now under certain circumstances, but that's going to be one of the key issues. We have to be able to reconceptualize, think of problems in different ways. Don't think about it as arranging dominoes on a chessboard. Think about it as every domino has to cover a red and a white. That is hard to do, but a skill that we're going to have to be able to do. We have to use common sense. How do we know that red hats don't matter in the hobbits and orcs problem? That's just common sense. But if common sense were common, computers would have it. They don't yet. We have to figure out how to do that. And I would say that all of the methods we're using for finding common sense, that they're all going to fail. But that doesn't mean they always have to fail. And then we have to be able to specify our own goals. Thanks. I will entertain questions. I want to highlight my book, which came out on Tuesday. It's available wherever books are sold. And with that, I'm going to stop the presentation and see if we can answer some questions. Okay. Q&A. Come on, you can do it. My Q&A thing doesn't want to come up. Okay. Does anybody know how to make the Q&A window come up? This is the second virtual conference I've been to this week, and the fourth one I've been to this year. I think there are still things to work on. Maybe somebody can ask me some questions.
So in the down, you will see capital Q and A. You have to just press, you just press that.
No, I don't. I'm clicking on it. It doesn't do anything.
I can ask the questions there. So
currently
we have about 10 questions there. So
okay.
About 1-3 is at the beginning of the talk. I think Rishabh Chaliji asked a question: what is be possible that Ray Cavalera's idea of, I don't know, is inspired from Herb Simmons' insight? And I think, oh my gosh, this is really okay. Let me see. Let me copy the question to you at the chat.
Yeah, I don't know why oh, I see why. It opened in the other window. Never mind. Okay.
Okay. So this is the first question. It's about,
would it be possible that Ray Kurzweil's idea of singularity is inspired from Herb Simon's insights at the Dartmouth conference? Actually not, although I'm sure it had something to do with it. Ray Kurzweil has this idea of the singularity, which is actually derived from I.J. Good. And I.J. Good's explosion is the notion of singularity. Kurzweil's idea is that computers will get so good that we can upload our consciousness to the computer and go on from there. And so we could live forever because we'd be computers rather than meat. I think he's wrong for lots of reasons. And the very first reason for the nearby future is that we have no idea, A, what consciousness is, B, how it's represented in the brain. We don't even know how neurons really work yet. So the likelihood of that coming close, I think, is nil. And I've got some other papers on singularity that I can be sharing. They were under review. They just got rejected bad taste. Okay.
We have, I think we have another question by Jordan Plume. The
Yeah,
question
I have that. I have that now.
You have that? Okay, you see that,
Yeah.
right?
Yeah,
okay.
I find I'm running two screens and now I have it. So what are the most promising AI projects involving unstructured data goals based on folding closed example? Would a breakthrough in this field lead to a significant advancement in general AI? Let me answer the second part first. A significant advancement in general AI is anything that we do that advances AI, period, is an advancement. Whether it's an advancement that will get us really closer to general artificial intelligence, I don't think so. I think that the idea of unstructured problems like driving cars, walking across rooms, Hans Moravec had what came to be called the Moravec paradox, that what people find difficult to do, like proving theorems, is easy for computers, and what people find easy to do, like recognizing faces, is hard for computers to do. We're making some progress on those. What I think it's going to take is rethinking how we think about those unstructured problems and how we solve them. For me, the most interesting thing we're working on right now is self-driving vehicles. That is where I think the most interesting development in artificial intelligence is going on. Is there any business application with the technology behind the chess case? I don't think so. What there is the idea that we have to think about things in a certain way in order to be able to solve them with a computer. So the Turing team, the Turing Prize team from 2018, deep learning, all of that was a new insight. Backpropagation was new insight in how to get neural networks to learn things. That was important. It took a human to be able to do it. Those things all have business applications. That's how we're doing all of our AI in business these days. But in order to have a general intelligence, we have to have an intelligence that will actually make those. Next one, can you talk a little bit about job opportunities? AI work replaced a lot of labor work. Yes. Okay. So AI right now, in the conventional sense, the way we're using it for the most part, is good at replacing specific tasks. So the area I do most of my work in is in computer security and email analytics. And that has replaced in the legal field a lot of part-time and temporary attorneys who don't practice in a courtroom, but rather read documents for their jobs. We need many fewer of them to read documents. So it certainly has an effect on that. It hasn't replaced lawyers in the kind of lawyers that are responsible for writing contracts and responsible for going to court, responsible for pursuing the cases. But some of the lower level people have been replaced. There will continue to be an evolution of jobs to be automated, as there has been for the last 400 years. And I think the way to think about this is, if they make a robot to replace me, what I'm going to do is, like the previous talk said, find some other disruptive technology, or I'm going to start building those robots and learn about that.
Okay, sorry for the interruption. I think, the question is, AI replace some, jobs, but he or she was asking the job opportunity for AI engineers and, maybe data scientists. Do you think?
Yes, well, there are opportunities. The first talk this morning was about maybe we don't need so many data scientists. Maybe we can replace the data scientists. But I think that what we need are the people who do the conceptual work. We don't need somebody to when I started off, which is, you can tell it's a long time ago, they used to have these mechanical calculators called Frieden calculators. And the way they would compute things is people who were then called computers would use these big hunky machines to solve problems like personality tests and personality profiles. Those people got replaced by computational devices. The movie Hidden Figures is about that. So people are getting replaced, but what we need are people who can think about how to do that reduction, not necessarily the people who can do the computations. So I think there are lots of opportunities for job opportunities. I think they require a higher level than being a mechanical cog in the wheel of industry.
Thank you. We are grateful for the time and effort you took to share your thoughts and experiences. We have some more questions, but if you have few minutes, if you have some more time, you can answer those questions in Q&A section. And
Okay.
Your years of research and your depth knowledge of topic seriously helped us to understand this topic very well. Thank you again, Herbert. Thank you.
Thanks.
Thank you, Herbert. You did a good talk.